Chapter 4, Subsonic Airflow. Airfoil terminology. Airfoil is a shape capable of producing lift with relatively high efficiency. Chord line is a straight line joining the centers of curvature of the leading and trailing edges of an airfoil. This is the chord line from the center of the curvature on the leading edge to the center of the curvature of the trailing edge. Now, chords is the distance between the leading and trailing edges measured along the chord line. So this is the chord. Angle of incidence. This is the angle between the wing root's chord line and the longitudinal axis of the aircraft. So the wing can be the root chord of the wing can be mounted with a little bit of an angle in respect of the longitudinal axis of the aircraft. Here it says the angle is fixed for the wing but may be variable for the tailplane. For the example, in the 737, the whole tailplane can move its angle of incidence. Then we have mean line, or camber line, is a line joining the leading and trailing edges of an airfoil, equidistant from the upper and lower surfaces. This is the mean camber line, the mean line. So it gives an average. Maximum camber. The maximum distance of the mean line from the chord line. Maximum camber is expressed as a percentage of the chord with its location as a percentage of the chord aft of the leading edge. Let's go 1 second to the illustration here. So this is the maximum camber, so the maximum distance from the chord line. So this is the chord line, and its location. This is location starting as a percentage of from the leading edge, as it was saying. So this is the maximum camber is located here approximately. I'm not sure about. This is the chord. This is half, like 40%. That's the location of the maximum camber. To continue, when the camber line lies above the chord line of an airflow, is said to have positive camber. So the curvature is positive on top of the camber line. And if the camber line is above the chord line, I mean, if the camber line is below the chord line, it's said to have negative camber. A symmetrical airfoil has no camber because the chord line and camber line are coincidental. So as we were saying, this is the maximum camber. This is a positive camber. It could be negative if it lies below the chord line. So it's important to know the maximum camber if it's above or below the chord line. So a wing can also be curved this below the chord line, or it could have no chords, no maximum camber, because it will be coincidental to the chord line. So once again, a symmetrical airfoil has no camber. Has no camber. Thickness and chord ratio. The maximum thickness or depth of an airfoil section, expressed as a percentage of the chord with its location as a percentage of the chord aft of the leading edge. So again, we calculate this percentage starting from the leading edge, and we'll say like 50%, 25% from the leading edge. The thickness and thickness distribution of the airfoil section have a great influence on its airflow characteristic. Again, this is the maximum thickness, the general depth of the airfoil, and its location, where is it located. So this is a great influence because it reduces the tube that we were talking about in the third chapter. So air is forced to accelerate because it reduces its the distance between the free airflow of air and the wing. Leading edge radius, this one right here. This is the radius of curvature of the leading edge. The size of the leading edge radius can significantly affect the initial airflow characteristic of an airfoil section. It can be small, can be bigger, and the air there is forced to accelerate or accelerate less. This is very important, relative airflow. It will be very important later, especially when we talk about induced drag. The relative airflow is the relative wind or free stream flow, and it has three qualities. Direction. Air parallel to and in the opposite direction of the flight path of the aircraft. In fact, the path of the center of gravity. The direction in which the aircraft is pointing is irrelevant. This is very important. So this is the air parallel to and in the opposite direction of the flight path of the aircraft. So the path that the aircraft is following. The aircraft can be pointing up, but still this path could be straight and level, for example. Condition. Air close to but unaffected by the presence of the aircraft. Its pressure, temperature and velocity are not affected by the passage of the aircraft through it. Magnitude, the magnitude of the relative airflow is the TAS, T-A-S, true airspeed. If airflow does not possesses all three of these qualities, it is referred to as effective airflow. Here we have total reaction, the resultant of all the aerodynamic forces acting on the airfoil section. We will talk about before. Total reaction. Lift is going this way, but drag is going this way, so the total reaction will be like this. If this would have been much bigger, total reaction would have been this way. So not creating much lift. Center of pressure. The point on the chord line through which lift is considered to act. Let's go back here. The center of pressure, it would be this one. It's here on the chord line. Lift is acting here, then drag. It's acting over there, and so the total reaction is this, but this will be center of pressure. Lift. This is the aerodynamic force which acts at 90 degrees to the relative airflow. This is very important to know that lift acts at 90 degrees to the relative airflow. Drag, the aerodynamic force which acts parallel to and in the same direction as the relative airflow, or opposite to the aircraft flight path. So drag always acts opposite to the aircraft flight path. Angle of attack, or alpha here, you can see it as called as aerodynamic incidence. This is the angle between the chord line and the relative airflow. So the chord line and the relative airflow. So a relative airflow comes from here. This is the path of the airflow. So exactly, it's written even here. So this is the path of the aircraft. This is the relative airflow. The angle between the chord line and the effective airflow is referred to as the effective angle of attack. So again, this is the angle between the chord line and the effective airflow. This is not the relative airflow, but it is the effective airflow. So, basics about airflow. When considering airflow velocity, it makes, of course, no difference to the pressure pattern if the aircraft is moving through the air or the air is flowing over the aircraft. It is the relative velocity which is the important factor. So to promote a full understanding, references will be made to both wind tunnel experiments where air is flowing over stationary aircraft or the opposite, aircraft is moving through stationary air. Three-dimensional airflow. The three-dimensional flow is the true airflow over an aircraft and consists of a hypothetical two-dimensional flow modified by various pressure differentials. Three-dimensional airflow will be examined later, but just to have a general idea. Two-dimensional airflow assumes a wing with the same airfoil section along the entire span with no span-wise pressure differential flow. So it will be the same at the chord and it will be the same at the tip of the airplane. So just to make it simple, when it makes no difference, we talk about two-dimensional airflow. Okay, two-dimensional airflow. As air flows towards an airfoil, it will be turned towards the lower pressure at the upper surface. This is the termed and called upwash. So as air flows towards an airfoil, it will be turned towards the lower pressure, which is above. This is the upwash, so it will be sucked in even before it meets the airflow, as we can see here. So air starts to bend and move to the area of low pressure even before meeting the leading edge, which, well, of course, it will spread up and down. It will create the wing, but even before that's the upwash. So after passing over the airfoil, the airflow returns to its original position and state, and this is the downwash. So downwash is inevitable. Basically, the after passing up, and it follows the wing curvature, and it goes back down to its original state. You can see here the upwash, so air bends even before. Increased local velocity, so this is the streamlines particles of air that could not cross each other. So if this is going up, this is going up, it follows and accelerates here and then decelerates. As we can see, it's flowing down again. So influence of dynamic pressure. As we can see here, this is an airfoil section at a representative angle of attack subject to a given dynamic pressure. If the static pressure on one side of a body is reduced more than one on the other side, a pressure differential now exists. So we need a pressure differential. That can be low pressure here, but low pressure here, but it's lower there, so it's a pressure differential. As we can see in figure 4.5 here, same airfoil at the same angle of attack, but subject to a higher dynamic pressure, so more flow of air, more indicated air speeds. If dynamic pressure is increased, the pressure differential will increase, of course. There is a higher area of low pressure here, so this is the same angle of attack, just the airfoil is going, the relative flow is faster here, so it's creating more lift. The pressure differential acting on the surface area will produce an upward acting force, lift. If the dynamic pressure is increased, the upward force will increase. So this is one factor. Same angle of attack and different dynamic pressure. So airplane can be flown at the same angle of attack, but if you speed up, if there's more air flowing through, it will have more lift. Now we can talk about the influence of angle of attack. So now there is a constant dynamic pressure, so constant speed, indicator airspeed. Increasing the angle of attack up to about 16 degrees will likewise increase the pressure differential, but will also change the pattern of pressure distribution. The airfoil profile presented to the airflow will determine the distribution of velocity and hence the distribution of pressure on the surface. This profile is determined by the airfoil geometry, thickness and distribution, camber and distribution, and angle of attack, which is the only thing that's variable here for the moment, because camber and distribution can be changed. But for the moment, let's say you're only mean to change the geometry is by changing the angle of attack, giving a constant speed. So the greatest positive pressure occurs at the stagnation point on the leading edge, where the relative flow velocity is 0. The stagnation point is located somewhere near the leading edge. As the angle of attack increases from -4 degrees, the leading edge stagnation point moves from the upper surface around the leading edge to the lower surface. It is at the front stagnation point where the airflow divides now to pass over and under the section. The pressure at the stagnation point is static plus dynamic. Of course, static is always there, and of course, it's dynamic pressure. The flow over the top of the section accelerates rapidly around the nose and over the leading portion of the surface, inducing a substantial decrease in static pressure in those areas, as we were talking about in chapter 3. The rate of acceleration increases with increase in angle of attack. So the more the angle of attack, the more the air accelerates over the top surface of the wing, creating more lift, up to about 16 degrees. Anything which changes the accurately manufactured profile of the leading portion of the surface can seriously disrupt airflow acceleration in this critical area. So ice, snow, frost, dirt, dense, even heavy rain. This is very important. This leading edge, this section, this part on the leading edge is very important. The pressure reduces continuously from the stagnation value through the free stream value to a position on the top surface where a peak negative value is reached. From there onwards, the flow continuously slows down again, and the pressure increases back to the free stream value in the region of the trailing edge. At angles of attack less than 8 degrees, the flow under the section is accelerated much less, reducing the pressure to a small negative value. So there is low pressure here, it's accelerated as well, but it will be the same. It will be less. Values less than 8 will be, there will be low pressure here, but it will be even lower here. This is not the case. This is -4. The pressure differential between the leading edge stagnation point and the lower pressure at the trailing edge creates a force acting backward, which is called form or pressure drag. Angle of attack -4 degrees. The decreasing pressure above and below the section are equal and no differential exists. There will be thus no lift force. This can be called the zero lift angle of attack. So basically at angle of attack 0, for example, still, because this is as a positive camber, creates more lift. There is a lower pressure on the top than the bottom. So to be equal, it has to be a negative angle of attack. So let's see the various angle of attack now. From 0 to 8 degrees, compared to free stream static pressure, there is a pressure decrease over the upper surface and lesser decrease over the most of the lower surface. For a cambered, positively cambered airfoil, there will be a small amount of lift, even at small negative angles, -4 degrees to 0 degrees. So there will still a little bit of lift, as we can see here, is much greater. Then from angle of attacks alpha 0 to 16 degrees, increasing the angle of attack increases the lift force because the acceleration of the airflow over the top surface is increased by the reduction in effective cross-sectional area of the local stream tube. As we were saying before, we have to imagine the stream tube here, and it reduces the cross-sectional area. So air is first to speed up. The reduced pressure peak moves forward as the angle of attack increases. This is also very important. So as angle of attack increases, so you can see here, the center of pressure is here, the peak. Then it moves here, and then it moves here to its maximum. The greatest contribution to overall lift comes from the upper surface. This is very important. It is both a force acting to lift the wing, but it's more what happens on the top, the low pressure that creates the wing. Pressure gradient. It is a change in air pressure over distance. The greater the difference in pressure between 2 points, the steeper the gradient. Favorable gradient is when air pressure is falling in the direction of airflow. So pressure should fall in the direction of the airflow. So there should be higher pressure and lower as we go down and backwards. So an example here, such as between the point of minimum pressure on the top surface and the trailing edge. The higher the angle of attack, the steeper the pressure gradient. At angles of attack higher than approximately 16 degrees, the extremely steep adverse pressure gradient prevents air that is flowing over the top surface from following the airfoil contour. And the previously smooth streamline flow will separate from the surface, causing the low pressure area on the top of the section to suddenly collapse. Any pressure differential remaining is due to the pressure increase on the lower surface only. So there will be no more low pressure here. If we have a little bit of lift, it's because there is a high pressure down, but that's not enough. In fact, this condition is known as the stall. So this is the pressure gradient. There is much more low pressure. It's not very well distributed over the distance. Here it is. Here acts a lot in this part and much less here. So the air is not able to follow curvature and it will separate. Center of pressure. The whole surface of the airfoil contributes to lift, but the point along the chord where the distributed lift is effectively concentrated is termed the center of pressure. Like you're lifting a wing with your fingers using a piece of like a rope. The location of center of pressure is a function of camber and section lift coefficient. Angle of attack. Angle of attack can change the CP. Now let's talk about how does it move. As the angle of attack increases from 0 to 16 degrees, the upper suction peak moves forwards. So the point at which the lift is effectively concentrated, the center of pressure will move forwards. The center of pressure moves forwards, and the magnitude of the lift force increases with increase in angle of attack until the stall is reached, when the lift force decreases abruptly and the center of pressure generally moves back along the chords. Let's note now that the center of pressure is at its most forward location just before the stall. So this is CL max, the maximum coefficient of lift. If you increase the angle of attack even more, as its maximum, it will move backwards. Aerodynamic force coefficient. A coefficient is a dimensionless number expressing degree of magnitude. An aerodynamic force coefficient is a common denominator for all aircraft of whatever weight, size, and speed. It doesn't matter, so it's not how much newtons of lift is producing, because it will be it's a coefficient, so it will be valid for all planes. So it is a number with no dimension expressing degree of magnitude. An aerodynamic force coefficient is a dimensionless ratio between the average aerodynamic pressure and the airstream dynamic pressure. By this definition, a lift coefficient, CL, is the ratio between lift divided by the wing planform area and dynamic pressure and the drag coefficient. And the drag coefficient is the ratio between drag divided by the wing planform area and dynamic pressure. So it's just a factor, it's a coefficient. It's the ratio between drag, which can be calculated, divided by the wing planform area, and its dynamic pressure, so will be valid at any speeds. The use of the coefficient of an aerodynamic force is necessary, since the force coefficient is an index of the aerodynamic force independent of area, density, and velocity. It is derived from the relative pressure and velocity distribution. It is influenced only by the shape of the surface and angle of attack, since this factor determine the pressure distribution. As we can see here, this is the percentage of the chord of the leading edge, with angle of attack increasing. It stays forward, it moves forward to its maximum, and if you increase again the angle of attack, it will start to move backwards and cause stall. Leading edge, trailing edge, it moves along the chord line. Development of aerodynamic pitching moments. The distribution of pressure over a surface is the source of aerodynamic moments as well as forces. There are two ways to consider the effects of changing angle of attack on the pitching moment of an airfoil. Changes in the magnitude of lift acting towards a moving center pressure, or more simply, changes in the magnitude of lift always acting through an aerodynamic center, which is fixed. What is an aerodynamic center? The aerodynamic center is a fixed point on the chord line and is defined as the point where all changes in the magnitude of the lift force effectively take place, and the point about which the pitching moment will remain constant at normal angles of attack. A nose-down pitching moment exists about the aerodynamic center. As we can see here, of course, the center of pressure is well behind. It will make the airplane pitch down. Aerodynamic center is the product of a force, the lift at the center of pressure, and the arm, the distance from the center of pressure to the aerodynamic pressure. Of course, the center of pressure here has a bigger arm. If the center of pressure moves here, there will be less pitching moment, as we can see here. Since an increase in angle of attack will increase the lift force, but also move the center of pressure towards the aerodynamic center, shortening the lever arm, the moment about the aerodynamic center remains the same at any angle of attack with normal range. As we can see here, there is much more moment because the center of pressure is well behind the aerodynamic center. If it moves forward, there will be less moment, but since the angle of attack is increased, there is more lift as well, so is the same moment, is the same force at the end. So remains the same here at any angle of attack in the normal range. When considering subsonic airflows of less than Mach 0.4, the aerodynamic center is located at the 25% chord point of any airfoil regardless of camber, thickness and angle of attack. The aerodynamic center is an aerodynamic reference point, the most direct application being to the longitudinal stability of an aircraft, which will be discussed later. So pitching moment for a symmetrical airfoil, the way it pitches. Note the change in pressure distribution with angle of attack for the symmetrical airfoil in figure 4.11. When at zero angle of attack, the upper and lower surface forces are equal and located at the same points. With an increase in angle of attack, the upper surface force increases while the lower surface force decreases. A change in the magnitude of lift has taken place, with no change in the center of pressure position. With an increase in angle of attack, the upper surface force increases while the lower surface force decreases, as we were saying. Angle of attack increases, so there's less pressure here. So this is a characteristic of symmetrical airfoils. Thus, the pitching moment about the aerodynamic center for a symmetrical airfoil will be 0. Pitching moment will be 0 at normal angles of attack. One of the big advantages of symmetrical airfoils. And finally, to summarize, airflow pattern and ultimately lift and drag will depend upon angle of attack, so airflow cross-sectional area change. The more the angle of attack, the lowest the cross-sectional area change, with that we've seen in chapter 3. Airfoil shape, thickness and camber, as well airflow cross-sectional area change. If the angle of attack increases, if the thickness or camber of the wing is bigger, there will be less space. The cross-sectional area will be smaller and air would accelerate. Air density, the mass flow of air, and the velocity as well, mass flow of air. The lift force is the result of the pressure differential between the top and bottom surface of an airfoil. The greatest contribution to overall lift comes from the top surface. Anything, ice in particular, but also frost, snow, dirt, and even water droplets, anything that changes the accurately manufactured profile of the leading portion of the upper surface can seriously disrupt airflow, acceleration in that area, and hence magnitude of lift force. An increase in dynamic pressure, indicated airspeed, will increase the lift force, and vice versa. As well, an increase in angle of attack will increase lift force, and vice versa. So as we will see this in the equation, Q, the dynamic pressure, or Q, or half the density times speed squared. If it's increased, it increased that angle of attack, which would be CL, coefficient lift, increased lift force. The center of pressure of a cambered airfoil moves forward as the angle of attack increases. The center of pressure of a symmetrical airfoil does not move under the influence of angle of attack within the confines of normal range. Throughout the normal range of angles of attack, the airfoil nose down pitching moment about the aerodynamic center will remain constant. As we said before, the arm can be lower, but the lift acting up is higher. The aerodynamic center is located at the quarter chord position for subsonic flow, 25% of the chord from the leading edge, at less than Mach 0.4. The coefficient of lift is the ratio between lift per unit wing area and dynamic pressure. So it's the ratio between lift divided by the wing area and the dynamic pressure. As the angle of attack increases from -4 degrees, the leading edge stagnation point moves from the upper surface around the leading edge all the way to the lower surface. The greatest positive pressure occurs at the leading edge stagnation point, where the relative flow velocity is 0. Form, or pressure drag, is the result of the pressure differential between the leading edge and trailing edge of an airfoil. So this is a pressure differential. This is less pressure on the leading edge and a little bit higher pressure on the trailing edge with a force that acts backwards. An increase in dynamic pressure, indicated airspeed, will increase form drag and vice versa. The coefficient of drag, CD, is the ratio between drag divided by unit wing area and dynamic pressure, same as coefficient of lift. And this ends chapter 4, subsonic airflow.